Hello and welcome to worked example 5.17 on page 223 in the section 5.2 heating effect of electric currents. In the circuit shown below, the EMF of the cell is 9.00 volts and the internal resistance is assumed negligible. A non-ideal voltmeter whose resistance is 500 kiloohms is connected in parallel to a resistor of 500 kiloohms. Part A, determine the reading of the ideal ammeter. Part B, a student is shown the circuit and assumes incorrectly that the voltmeter is ideal. Estimate the resistance the student would calculate if he were to use the current in A. Okay, so in order to answer this, we got to really understand what's meant by ideal ammeter and ideal voltmeter. So if you recall from the lesson, an ideal ammeter should only allow all the current to move through without resisting it at all. So an ideal ammeter has a resistance value of 0. And so the fact that we are told that this is an ideal ammeter means that this does not contribute to the resistance of the circuit. If it did, you would be given a resistance value for this, and then you would treat it like any other circuit element. Now, what about an ideal voltmeter? The idea with the voltmeter is that you check the voltage on one side of the resistor and you check the voltage on the other side, and well, you take the difference. You subtract V2 from V1. So what you don't want is that when the current comes out of the battery for it to split and some of it to go through the voltmeter and the rest to go through the resistor. You want all of it to go through the resistor. Unfortunately, there's no such thing in real life as a voltmeter with infinite resistance, but it can be made very, very high. Unfortunately, in this case, it's the exact same resistance as the resistor. So when the electricity comes, so even though the the electrons are coming from this right side, we know that by the definition of current, I have to draw this as if a positive charge was moving through the circuit. So anyways, let's just do that. So if that's the current coming out of the circuit, right, so it's coming out of the positive side of the battery, goes through the ammeter. When it gets to this junction, it splits. And it splits according to the various resistances. Wherever there's less resistance, more current will go through that, right? It's just logical. And so then the currents meet up at this junction, they merge, and then they move back to the battery as the single original current. Now, how much is it going to split by? Well, if this was a very high resistance, as we would expect it to be and assume it to be, very little would go through this, and most of it would go through R, as we would want. However, since they are the same resistance, that means the current is going to split 50-50. All right, so ideally, a voltmeter has a resistance that is extremely high and theoretically, ideally, infinite. Okay, so let's figure out the reading of this ideal ammeter. So what that means is we're trying to figure out the current through the circuit because the ammeter is going to measure the total current that's coming out of the battery. So we are looking for, therefore, I sub t. So this is really I sub t, the total current. Now using Ohm's law tells us that V is equal to I times R. So if we rearrange that for I, it's equal to V divided by R. What's the voltage? The voltage is the voltage coming from the battery. So we call that the EMF, epsilon. We divide that by the total resistance. So this is total voltage, total current. The total resistance, so we just have to figure that out. Now, some of you might look at this and say, well, this is 500 kiloohms, that's 500 kiloohms. Since the electrons are getting split exactly in half, this could be replaced by an equivalent resistance of exactly half of one of them. And if you can see that, that is fantastic. And that will serve you very well for multiple choice questions where you don't have to show work. In questions like this where you do have to show work, well, you gotta show work. So we're going to call this resistor R1 and the voltmeter R2, because after all, it is its own resistor. So let's calculate the total resistance, which is effectively R12. Since they are in parallel, 1 over R12 is equal to 1 over R1 plus 1 over R2. So 1 over 500 kiloohms. I'll convert the kilo at the very end. So 1 over 500 kiloohms is 1 over R12. Okay, common denominator is 500 kiloohms. So the numerator becomes 2. 500 kilo ohms is 1 over R12. Flip both fractions, and we're going to get R12 over 1 is equal to 500 kilo ohms divided by 2. That's 250 kilo ohms. So again, those of you who had that idea from the start, you were absolutely right, but you got to show your work. So 250 kilo ohms, which is the equivalent of 250,000 ohms. So this is our total because these two are the same thing. So that gets plugged in up here. All right, so that is 250,000 ohms. Epsilon, we're told, is 9 volts. So 9 volts divided by 250,000 ohms. So that's 3.6 times 10 to the negative 5 amperes. Now, all they've done in the book is they've said, well, let's just make this look nice, because if we move this to 10 to the minus 6, all of a sudden I've got the prefix micro. And so if I want to make this times 10 to the minus 6, that means instead of moving the decimal 5 spaces to the left, I have to move it 6. And in order to do that, I would have to stick the decimal right after the 6. So this could be 36 times 10 to the minus 6 amperes, and times 10 to the minus 6 is the prefix micro. And so we can just write this nicely as 36 microamperes. So that is the current that the ammeter measures. So let's just put a therefore statement. Therefore, the ideal ammeter has a reading of 36 microamperes. Okay. The part B of the question, so this was all part A. Part B says the student is shown the circuit and assumes incorrectly that the voltmeter is ideal. So they thought that this actually had infinite resistance, so none of the electricity actually went through this. Estimate the resistance that the student would calculate if he were to be using the current in part A. So this is actually not a difficult part of the problem. If this thing really did have infinite resistance, that means none of this current would have actually gone through here. All of it would have gone through R, so it would have just exactly gone through this counterclockwise loop, right? So we had the total voltage from the battery, we calculated the total current, and therefore if there's only one resistor, that means this is the only one. Now keep in mind that we figured out the value for this current, which we are asked to use, right, the current in A. This current came from the fact that we assumed a resistance of 250 ohms, or rather an equivalent resistance of 250 kilo ohms. All right, so what that means is it's equivalent to replacing this whole system with a single resistor of 250 kilo ohms. And so therefore that is the resistance that the student would calculate. All right, so we can say something like this. Since the current in the circuit was determined using the equivalent resistance of R and the voltmeter, in brackets we can say, which was 250 kilo ohms. So since the current in the circuit was determined using the equivalent resistance of R in the voltmeter, which was 250 kilo ohms, the current stayed the same. And so did the EMF. Therefore, this resistance now needed to come from R only, right? So no voltmeter. Therefore, the student would incorrectly calculate the resistance as 250 kilo ohms. And that's really all it is. So just being able to explain that in a logical sense. So that is it for worked example 5.17.